All right, another thing you might want to do is see Rust in all its glory, because whatever you're doing in C or C++, you probably should be doing your new development in Rust, or at least you should consider it. It will save you a lot of problems. So you have to install Rust, and then you can make Hello World. I think I've already got it on my machine. Let me find my cloud machine, which is here. Okay, let's go home, and then let's try, not here, okay. Oh, I don't have it. All right, I have to do this. All right, let's try make a directory, CD and nano, okay. We make these so they fit on the screen, that's fine. All right, so, all right, here's my Rust Hello World program, which as you can see is not that different than what would it look like in C. A little bit hard to read in here, but just print line, main function, usual sort of thing. All right, now let's see if I can compile it. I may have to install Rust on this cloud machine. I don't remember if I've got it on this one. I'm thinking I don't. All right, so let me install it. Here's the Rust compiler. Just these 3 commands. There we go. And everything's nice and fast because I'm in the cloud, so it's just going from Google to the servers at the speed of Google, not at all limited by my local speed.
You're missing one of the PHP flags in the list of
Oh,
flags.
well, thanks for telling me. Okay.
200.2.
Which one?
CS 200.2.
Thanks. Okay, good. I'll fix that after this video. Thank you. All right, good. All right, now I should be able to compile this thing. All right, and then I can run it with /hello. And it just says hello world, so I have Rust and it's working. All right, now we can make a insecure app with one of the simple flaws. Okay, so here's, all right, here you get to see Rust variables. If you don't specify a variable, it will be a signed 32-bit integer. If you do specify, you can specify, put a colon. This is an unsigned 32-bit integer. So I specify an unsigned 32-bit integer, and I try to set it to -5. And when you compile it, it tells you, cannot apply unary operator to unsigned integer. This is why developers love it. If you make a mistake, it tells you, and you get to fix it. So then let's move on to adding numbers. Integer overflow in C. So CD and nano OVC. Right, so here's an integer overflow in C. All right, I got used to writing C long ago, of course, and I only recently began to appreciate how utterly stupid this is. Here I define a character variable, then I set it to 230. Now right now, this makes no sense at all. A character variable should store a character. And nowadays, characters are not integers. They are up to 4 bytes of Unicode because there's more than English in the world. And even if it was only English, the ASCII characters only go up to 127. So how am I putting 230 in a character variable? I got used to this, so it was just instinctual to me that a character was a byte and a string was a byte array. But that is in fact complete garbage. I had to unlearn that as I moved into the modern world. A string should be a series of characters, each of which is Unicode characters going up to 4, and a byte array is a list of bytes, and they're totally different things. But anyway, I can do that. Now I'm going to add to it a series of numbers 1, 2, 3, 4, 5 to that thing once it started. So I'll save this, and I can compile it as usual. And when you run it, X is 231, X is 245, 251, X is 2, X is 10, X is 19. This is the kind of cruelty that hurts your developers, right? I added to the number and it got smaller. I was supposed to know that would happen and remember that would happen. And you know, in the early days of C, like 1979, it was a slightly easier way to write assembler, and the programmers all understood exactly at the assembly language level where every bit was going. And they expected you to write C with that level of knowledge about the hardware, but that's not the way modern developers are. They're thinking about abstract quantities, and so when you give them a number and they add to it, they expect it to get bigger. And Rust will not do that. Rust will tell you, it can't get any bigger, you have a mistake. So that's one that Rust will fix. And if you make that same program in Rust, which is here, the code looks almost exactly the same. But you tell it, you have to tell it a variable is mutable. If you don't, it's immutable. Then you have to tell it what it is. This is an unsigned 8-bit integer. So now setting it to 230 is reasonable. I did not ever pretend it was a character. It's an unsigned 8-bit integer. Now I make the same loop and I add to it. And when you compile that in Rust and run it, it goes up to 251 and then it crashes and said you attempted to add with overflow. So again, you will find out if your code is going to do something crazy. And of course, the one that is responsible for almost all the flaws in Windows XP and earlier, the string buffer overflow. So let's do that one. Nano strov.c. Gotta spell my nano better. All right, so here's a buffer overflow. And you can see here I define two strings. They're each 5 bytes long, so they have 4 bytes in the room for the null byte at the end, which is another, by the way, terrible decision of C developers. So now I have 4 bytes. I store 4 letters twice, and I print their addresses. Now I read in a new value for string 2 and print them out again. So if I run this one, okay, compilation terminated. Okay, I must have spelled straw, but I didn't put a C in it, all right. There we go. All right. Okay, so I have a new value for string 2. I can put it CCCC, and then it works. String 1 contains A, string 2 now contains CCC, so that's fine. But if I run it again, first string 1 contains A's and string 2 contains B's, but if I put in a lot of C's, I got to get rid of that space that I got put in there somehow. Okay. If I put in like 10 or 20 C's, then I entered a new value for string 2. String 1 now contains a bunch of C's. String 2 now contains a bunch of C's because it overrode the null terminator. So how is your developer supposed to not go insane at this point? I read in data for string 2 and it changes string 1. This is madness. How was I supposed to understand where those were stored in memory, when it would overflow? Why did it let me do this anyway? This is the kind of cruelty that drives you insane, and you have endless memory corruption vulnerabilities caused by this. And people have been for decades saying, oh, developers just need to learn to code better. And I say, well, we tried that. That is not working. Developers never learn to foresee all these things. And so the solution, which is gaining popularity, is, of course, Rust. If you do this in Rust, Rust is almost as fast and small as C. I think some people claim it is entirely as small and fast as C after compilation, so you don't need to put up with C for performance, but you write the same program in Rust, and by the way, it looks very much the same, and then when you run it, okay, enter a new value for string 1. String 1 contains AAA, string 2 contains BBB, and they showed me in different order, so I can put in a whole lot of C's here for string 1. And it adds them to the A's and doesn't change string 2. So, and you can go into the debugger and look at the memory, and that's what goes on if you go here, and you will find that the way it does it is, it does not store the strings directly in the stack, it stores a pointer to them. And then when you make it bigger, it moves the pointer to point to an area with enough room to store the new bigger string, just like it ought to. So you're no longer driving your developers insane. When I tell it, store a string that is this long, it allocates enough memory to store a string that long and doesn't destroy my program the way C does. So that's one of the examples of why Rust is so much better. And there are others. Now, the command injection vulnerability is one where you actually do the horrible thing of using one language to write code that goes to another language. So let's talk about this one. This is a very common flaw, and let me go here. All right. So here, what I did was I wanted to do a ping, like your router configuration page has an option test the internet by sending a ping. So it will create a line. You asked for an IP from the user, and then it creates a line of code called ping minus C1 followed by IP. This is a terrible practice. If you can't figure out how to write whatever you're doing in one language, You create a line of code and feed it to another interpreter for another language. This is how you create command injection vulnerabilities. Because of course, you're sending data that came from the user without filtering it. So if I compile this one, I can put an IP of, say, 1.1.1.1, and then it will ping 1.1.1, so that works. But I can, of course, do this. I can put in 1.1.1.1, semicolon, who am I, semicolon, ls, because it's just creating a line of bash code, and so it executes who am I and ls. So I have now got, whoever I revealed that page to now has code injection on my server. And this is very common, easy to exploit. And this is bash command injection like SQL injection that you see and otherwise. So that's the point. And this is not fixed by Rust. If you really want to do this horrible thing of making a line of code and passing it off to another interpreter, you can do that in Rust and it will still have this flaw. Rust cannot save you in this case because you told it, make this line of code and execute it. So that's one thing to mention. Now, the next thing I wanted to point out is the other part of this Rust thing is the slightly more sophisticated ones of dangling pointers and memory links. And this is because of another bit of cruelty in C. Now, the heap, as you know, is used for temporary storage of data when you're going to allocate some space, store something, and you want to deallocate it later. And in C, you have to use malloc to reserve space on the heap, and then you have to use free to get rid of it later. And the problem is you have to do three things. You have to allocate it with malloc, you have to free it with free, and you have to set it to null. If you forget to do all three of those things correctly, you have a dangling pointer. If you don't free it, you have a variable pointing to memory that is no longer allocated for that purpose, and if you write to it or read from it, you're going to have unexpected results. If you fail to set it to null, the pointer, even after freed, still points to memory that can be used. And problem is, as you have code and subroutines and other subroutines, it's entirely possible that the free is in a different routine and somehow it gets done twice or not at all, and that leads to a dangling pointer memory corruption. So you can demonstrate this in C. In Rust, it's incredibly simple. You don't do it this way. In Rust, you use this thing called box to reserve space, and the rule is you figure out the scope of the variable, where that curly brace is. And when you leave scope, it automatically frees and deletes the pointer. You don't have to remember to free it or null it. So you can't create a dangling pointer or anything. It's beautiful and simple, and it spares your programmers from suffering with all that stuff. So that's what I wanted to show you. And I think there's also, you can also do the dangling pointer, another version of the same thing. Anyway, so these might be the ones of greatest interest to you if you're interested in improving C development and maybe moving towards Rust. Here, let me stop this recording.